Imagine throwing a ball into the air. It arcs gracefully before falling back to the ground, following a path that seems almost predestined. But what determines this path? Why does the ball not take a different route, say, a zigzag or a loop? The answer lies in one of the most profound principles in physics, the principle of least action. This principle reveals that nature, in its infinite complexity, chooses the path of least effort, a path that minimizes a quantity known as action. In this video, we will explore what the principle of least action is, how it was developed, and why it is considered one of the most elegant formulations in physics. The idea that nature follows a path of minimal effort has intrigued thinkers for centuries. However, it wasn't until the 18th century that this concept took a rigorous form. French mathematician Pierre-Louis Maupertuis proposed that nature is thrifty in all its actions, suggesting that physical phenomena occur in a way that minimizes some quantity. Though his initial formulation was imprecise, it sparked a revolutionary idea. Mathematicians like Leonhard Euler and Joseph-Louis Lagrange built upon this foundation, developing advanced tools to find paths that optimize certain quantities. Lagrange applied this to mechanics, introducing a function known as the Lagrangian, and demonstrating how a system's motion could be derived from it. Later, William Rowan Hamilton refined the principle further, cementing its place as a cornerstone of theoretical physics. To grasp the principle of least action, we need to understand a few key ideas from classical mechanics, explained here in simple descriptive terms. Lagrangian. This is a function that captures the dynamics of a system. For many systems, it is the kinetic energy, the energy of motion, minus the potential energy, which is the energy due to position. Action. The action is the total of the Lagrangian accumulated over time between 2 points. Picture it as adding up the Lagrangian at every moment along the path from the starting point to the end. The principle of least action states that the actual path a system takes between 2 moments in time is the one where the action remains nearly unchanged if the path is slightly adjusted. Often this means the action is as small as possible, though it can sometimes be a maximum or a balanced point. This method differs from Newton's laws, which describe motion moment by moment. Instead, the principle of least action looks at the entire journey at once, finding the path that best balances this special quantity called action. Let's explore the principle with 2 clear examples. A free particle. Imagine a particle moving through space with no forces acting on it. Its Lagrangian is just its kinetic energy. The principle of least action seeks the path where the total action stays nearly the same, even if the path shifts slightly. This results in the particle moving in a straight line at a steady speed, matching what we'd expect from Newton's idea that an object keeps moving unless something stops it. A particle in gravity. Now picture a particle falling under Earth's gravity. Its potential energy depends on how high it is, so the Lagrangian is the kinetic energy minus the potential energy. When we apply the principle of least action, the path that keeps the action steady shows the particle speeding up downward at a constant rate. This aligns perfectly with how we see objects fall faster as they drop toward the ground. In both examples, the principle of least action gives us the same outcomes as Newton's laws, but it does so in a beautifully unified way. Significance and elegance. The principle of least action is far more than a handy tool. It's a foundation that ties together many areas of physics. It works for classical mechanics. It recreates Newton's laws, as we've seen in the examples. Electromagnetism. The behavior of electric and magnetic fields follows a similar idea of optimizing action. General relativity. Einstein's theory of gravity comes from finding the best action for space-time. Quantum mechanics. In the quantum world, this principle helps determine the likelihood of different paths for particles. This wide reach shows its elegance. One simple idea explains so many different things. Plus, it connects to the concept that when nature has certain symmetries, like not changing over time or across space, it leads. The principle of least action is one of the most beautiful and powerful ideas in physics. It captures nature's rules in a single, elegant statement. The universe follows the path where action is balanced. By looking at the whole path rather than just the forces at each step, it uncovers the symmetry and efficiency in how everything works. From a ball falling to the ground to the curving of spacetime, this principle lights the way for understanding nature's elegance. As Maupertuis might put it, nature is thrifty, and in that thrift we find its stunning beauty.